discovering the laws of motion. When Archimedes died, the mathematical study of nature nearly died along with him. 1800 years passed before a new Archimedes appeared. In Renaissance Italy, a young mathematician named Galileo Galilei picked up where Archimedes had left off. He watched how things moved when they flew through the air or fell to the ground, and he looked for numerical rules in their movements. He did careful experiments and made clever analyses. He timed pendulums swinging back and forth and rolled balls down gentle ramps and found marvelous regularities in both. Meanwhile, a young German mathematician named Johannes Kepler studied how the planets wandered across the sky. Both men were fascinated by patterns in their data and sensed the presence of something far deeper. They knew they were onto something, but couldn't quite make out its meaning. The laws of motion they were discovering were written in an alien language. That language, as yet unknown, was differential calculus. These were humanity's first hints of it. Before the work of Galileo and Kepler, natural phenomena had rarely been understood in mathematical terms. Archimedes had revealed the mathematical principles of balance and buoyancy in his laws of the lever and hydrostatic equilibrium, but those laws were limited to static, motionless situations. Galileo and Kepler ventured beyond the static world of Archimedes and explored how things moved. Their struggles to make sense of what they saw spurred the invention of a new kind of mathematics that could handle motion at a variable rate. It addressed the type of change that keeps changing, like a ball gaining speed as it rolls down a ramp or the planets speeding up as they move closer to the sun and slowing down as they recede from it. In 1623, Galileo described the universe as this grand book ... which stands continually open to our gaze, but cautioned that the book cannot be understood unless one first learns to comprehend the language and read the letters in which it is composed. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures without which it is humanly impossible to understand a single word of it. Without these, one wanders about in a dark labyrinth. Kepler expressed even greater reverence for geometry. He described it as co-eternal with the divine mind and believed that it supplied God with patterns for the creation of the world. The challenge for Galileo, Kepler, and other like-minded mathematicians of the early 17th century was to take their beloved geometry, so well suited to a world at rest, and extend it to a world in flux. The problems they faced were more than mathematical. They had to overcome philosophical, scientific, and theological resistance as well. The world according to Aristotle. Before the 17th century, motion and change were poorly understood. Not only were they difficult to study, they were considered downright distasteful. Plato had taught that the object of geometry was to gain knowledge of what eternally exists, and not of what comes for a moment into existence and then perishes. His philosophical contempt for the transitory returned on a grander scale in the cosmology of his most illustrious student, Aristotle. According to Aristotelian teaching, which dominated Western thought for almost 2 millennia, and which Catholicism embraced after Thomas Aquinas expunged its pagan parts, the heavens were eternal, unchanging, and perfect. Earth sat motionless at the center of God's creation, while the sun, moon, stars, and planets revolved around it in perfect circles, carried along by the rotation of the heavenly spheres. According to this cosmology, everything in the terrestrial realm below the moon was corrupted and plagued by rot, death, and decay. The vagaries of life, much like the falling of leaves, were by their very nature fleeting, erratic, and disorderly. Although an Earth-centered cosmology seemed reassuring and commonsensical, the motion of the planets presented an awkward problem. The word planet means wanderer. In antiquity, the planets were known as the wandering stars. Instead of maintaining their places in the sky, like the fixed stars in Orion's belt and the ladle of the Big Dipper, which never moved relative to one another, the planets appeared to drift across the heavens. They progressed from one constellation to another as the weeks and months went by. Most of the time they moved eastward relative to the stars, but occasionally they appeared to slow down, stop, and go backward, westward, in what astronomers called retrograde motion. Mars, for example, was seen to move in retrograde for about 11 weeks over the course of its nearly 2-year circuit around the sky. Nowadays, we can capture this reversal photographically. In 2005, the astrophotographer Tunç Tezel took a series of 35 snapshots of Mars, each about a week apart, and aligned the images to the stars in the background. In the resulting composite, the 11 dots in the middle show Mars moving in retrograde. Today we understand that retrograde motion is an illusion. It's caused by our vantage point on Earth as we pass the slower-moving Mars. It's like what happens when you pass a car on the highway. Imagine driving on a long highway out in the desert, with mountains off in the distance. As you approach a slower car from behind, It looks like it's moving forward when viewed against the backdrop of the mountains. But when you pull alongside and pass it, the slower car momentarily seems to move backward relative to the mountains. Then, once you get far enough ahead of it, the car appears to move forward again. This kind of observation led the ancient Greek astronomer Aristarchus to propose a sun-centered universe almost 2 millennia before Copernicus did. It neatly solved the riddle of retrograde motion. However, a sun-centered universe raised questions of its own. If the Earth moves, why don't we fall off? And why do the stars appear fixed? They shouldn't. As the Earth moves around the Sun, the distant stars should appear to shift their positions slightly. Experience shows that if you look at something far away and then move and look again, the position of that faraway object appears to shift when viewed against a more distant backdrop. This effect is called parallax. To experience it, hold your finger far out in front of your face, close one eye, then the other. Your finger seems to shift sideways against the backdrop when you switch eyes. Likewise, as the Earth moves around the Sun in its orbit, the stars should shift their apparent positions against the background of even more distant stars. The only way out of this paradox, as Archimedes himself realized when reacting to Aristarchus's sun-centered cosmology, would be if all the stars were immensely distant, effectively infinitely far away from the Earth. Then the planet's motion would produce no detectable shift, because the parallax would be too small to be measured. This conclusion was hard to accept at the time. No one could imagine a universe so immense with stars so remote, much farther away than the planets. Today we know that is exactly the case, but back then it was inconceivable. So the Earth-centered cosmology, for all its faults, seemed like the more plausible picture. Suitably modified by the ancient Greek astronomer Ptolemy with epicycles, equants, and other fudge factors, the theory could be made to account reasonably well for planetary motion, and it kept the calendar in line with seasonal cycles. The Ptolemaic system was clunky and complicated, but it worked well enough to last into the late Middle Ages. 2 books published in 1543 marked a turning point, the beginning of the scientific revolution. In that year, the Flemish doctor Andreas Vesalius reported the results of his dissections of human cadavers, a practice that had been forbidden in earlier centuries. His findings contradicted 14 centuries of received wisdom about human anatomy. In that same year, the Polish astronomer Nicolaus Copernicus finally allowed publication of his radical theory that the Earth moved around the Sun. He'd waited until he was near death and died just as the book was being published, because he'd feared that the Catholic Church would be infuriated by his demotion of the world from the center of God's creation. He was right to be scared. After Giordano Bruno proposed, among other heresies, that the universe was infinitely large with infinitely many worlds, he was tried by the Inquisition and burned at the stake in Rome in 1600. Enter Galileo. Into this climate, as authority and dogma were being challenged by dangerous ideas, Galileo Galilei was born on February 15, 1564 in Pisa, Italy. The eldest son of a once noble family now down on its luck, Galileo was pushed by his father toward a career in medicine, a much more lucrative profession than his father's own field of music theory. But Galileo soon found his passion was mathematics. He studied Euclid and Archimedes and mastered both. Though he never finished his degree, his family couldn't afford the tuition. He continued to teach himself math and science, got a lucky break as a temporary instructor at Pisa, and gradually rose through the academic ranks as a professor of mathematics at the University of Padua. He was a brilliant lecturer, clear and irreverent with a caustic wit. Students flocked to his classes to hear him. He met a vivacious and much younger woman named Marina Gamba, with whom he had a long and loving but illicit relationship. They had 2 daughters and a son together but did not marry. It would have been considered dishonorable for him, given Marina's youth and lower social standing. With the strain of his meager salary as a math teacher, the cost of raising their 3 children, and the additional responsibility to provide for his unwed sister, Galileo felt forced to place his daughters in a convent, which broke his heart. His elder daughter, Virginia, was his favorite, the joy of his life. He later described her as a woman of exquisite mind, singular goodness, and most tenderly attached to me. When she took her vows as a nun, she chose Sister Maria Celeste as her religious name in honor of the Virgin Mary and her father's fascination with astronomy. Galileo is perhaps most often remembered today for his work with the telescope and as a champion of the Copernican theory that the Earth moves around the Sun, a contradiction of the views of Aristotle and the Catholic Church. Although Galileo did not invent the telescope, he improved it and was the first to make great scientific discoveries with it. In 1610 and 1611, he observed that the moon had mountains, the sun had spots, and Jupiter had 4 moons. Others have been discovered since then. All these observations flew in the face of the prevailing dogma. Mountains on the moon meant it was not a glistening, perfect orb, contrary to Aristotelian teaching. Likewise, spots on the sun meant it was not a perfect celestial body. It was marred by blemishes. And since Jupiter and its moons looked like a little planetary system of its own, with 4 small moons orbiting around a bigger central planet, then clearly not all heavenly bodies revolved solely around the Earth. Furthermore, those moons managed to stay with Jupiter as they all moved across the sky. At the time, one of the standard arguments against heliocentricity was that, if the Earth was orbiting the Sun, it would leave the Moon behind, but now Jupiter and its moons showed that this reasoning must be false. This is not to say that Galileo was an atheist or irreligious. He was a good Catholic, and believed that he was revealing the glory of God's work by documenting it as it truly was rather than by relying on the received wisdom of Aristotle and his later scholastic interpreters. The Catholic Church, however, did not see it this way. Galileo's writings were condemned as heresy. He was brought before the Inquisition in 1633 and ordered to recant, which he did. He was sentenced to life in prison, a punishment immediately commuted to permanent house arrest in his villa in Arcetri in the hills of Florence. He looked forward to seeing his beloved daughter Maria Celeste, but soon after his return, she fell ill and died at only 33 years of age. Galileo was bereft and for a while lost all interest in work and life. He spent his remaining years under house arrest, an old man losing his vision and racing against time. Somehow, within 2 years of his daughter's death, he found the strength within himself to summarize his unpublished investigations of motion from decades earlier. The resulting book, Discourses and Mathematical Demonstrations Concerning 2 New Sciences, was the culmination of his life's work and the first great masterpiece of modern physics. He wrote it in Italian rather than Latin so that it could be understood by anyone, and arranged for it to be smuggled out to Holland, where it was published in 1638. Its radical insights helped launch the scientific revolution and brought humanity to the cusp of discovering the secret of the universe, that the great book of nature is written in calculus, falling, rolling, and the law of odd numbers. Galileo was the first practitioner of the scientific method. Rather than quoting authorities or philosophizing from an armchair, he interrogated nature through meticulous observations, ingenious experiments, and elegant mathematical models. His approach led him to many remarkable discoveries. One of the simplest and most surprising is this: the odd numbers 1, 3, 5, 7, and so forth are hiding in how things fall. Before Galileo, Aristotle had proposed that heavy objects fall because they are seeking their natural place at the center of the cosmos. Galileo thought these were empty words. Instead of speculating about why things fell, he wanted to quantify how they fell. To do so, he needed to find a way to measure falling bodies throughout their descent and keep track of where they were moment by moment. It wasn't easy. Anyone who has dropped a rock off a bridge knows that rocks fall fast. It would take a very accurate clock, of a kind not available in Galileo's day, and several very good video cameras, also not available in the early 1600s, to track a falling rock at each moment of its rapid descent. Galileo came up with a brilliant solution. He slowed the motion. Instead of dropping a rock off a bridge, he allowed a ball to roll slowly down a ramp. In the jargon of physics, this sort of ramp is known as an inclined plane, although in Galileo's original experiments, it was more like a long, thin piece of wooden molding with a groove cut along its length to act as a channel for the ball. By reducing the slope of the ramp until it was nearly horizontal, he could make the ball's descent as slow as he wished, thus allowing him to measure where the ball was at each moment, even with the instruments available in his day. To time the ball's descent he used a water clock. It worked like a stopwatch. To start the clock he would open a valve. Water would then flow steadily at a constant rate straight down through a thin pipe and into a container. To stop the clock he would close the valve. By weighing how much water had accumulated during the ball's descent, Galileo could quantify how much time had elapsed to within 1/10 of a pulse beat. He repeated the experiment many times, sometimes varying the tilt of the ramp, other times changing the distances rolled by the ball. What he found, in his own words, was this: the distances traversed, during equal intervals of time, by a body falling from rest, stand to one another in the same ratio as the odd numbers beginning with unity. To spell out this law of odd numbers more explicitly, let's suppose the ball rolls a certain distance in the first unit of time. Then, in the next unit of time, it will roll 3 times as far, and in the next unit of time after that, it will roll 5 times as far as it did originally. It's amazing. The odd numbers 1, 3, 5, and so on are somehow inherent in the way things roll downhill. And if falling is just the limit of rolling as the tilt approaches vertical, the same rule must hold for falling. We can only imagine how pleased Galileo must have been when he discovered this rule. But notice how he phrased it: with words and numbers and proportions, not letters and formulas and equations. Our current preference for algebra over spoken language would have seemed cutting-edge back then, an avant-garde, newfangled way of thinking and speaking. It's not how Galileo would have thought or expressed himself, nor would his readers have understood him if he had. To see the most important implication of Galileo's rule, let's look at what happens if we add consecutive odd numbers. After 1 unit of time, the ball has traveled 1 unit of distance. After the next unit of time, the ball has traveled another 3 units of distance, for a total of 1 plus 3 equals 4 units traveled since the motion started. After the third unit of time, the total becomes 1 plus 3 plus 5 equals 9 units of distance. Notice the pattern. The numbers 1, 4, and 9 are the squares of consecutive integers. 1 squared equals 1, 2 squared equals 4, 3 squared equals 9. So Galileo's odd number rule seems to be implying that the total distance fallen is proportional to the square of the time elapsed. This charming relationship between odd numbers and squares can be proved visually. Think of the odd numbers as L-shaped arrays of dots, then nestle them together to form a square. For example, 1 plus 3 plus 5 plus 7 equals 16 equals 4 times 4, because we can pack the first 4 odd numbers together to make a 4 by minus 4 square. Along with his law about the distance traversed by a falling body, Galileo also discovered a law for its speed. As he put it, the speed increases in proportion to the time of falling. What's interesting about this is that he was referring to the speed of the body at an instant, a seemingly paradoxical concept. He took pains in 2 New Sciences to explain that when a body falls from rest, it doesn't jump suddenly from 0 speed to some higher speed, as his contemporaries thought. Rather, it passes smoothly through every intermediate speed, infinitely many of them, in a finite amount of time, starting from 0 and continuously gaining speed as it falls. So in this law of falling bodies, Galileo was instinctively thinking about instantaneous speed, a differential calculus concept that we'll examine in Chapter 6. At the time, he couldn't make it precise, but he knew what he meant intuitively. The art of scientific minimalism. Before we leave Galileo's inclined plane experiment, let's be sure to notice the artistry behind it. He coaxed a beautiful answer out of nature by asking a beautiful question. Like an abstract expressionist painter, he highlighted what he was interested in and cast the rest aside. For example, in describing his apparatus, he says he made the groove very straight, smooth, and polished, and rolled along it a hard, smooth, and very round bronze ball. Why was he so concerned with smoothness, straightness, hardness, and roundness? Because he wanted the ball to roll downhill under the simplest, most ideal conditions he could contrive. He did everything he could to reduce the potential complications coming from friction or from the ball's collisions with the sidewalls of the groove, which could occur if the channel was not straight, or from the ball's softness, which could cause the ball to lose energy if it deformed too much, or from anything else that could cause deviations from the ideal case. Those were the right aesthetic choices, simple, elegant, and minimal. Compare Aristotle, who got the law of falling bodies wrong because he was led astray by complications. He claimed that heavy bodies fell faster than light ones with speeds proportional to their weight. That's true of tiny particles sinking in a very thick, viscous medium like molasses or honey, but not of cannonballs or musket balls dropped through the air. Aristotle seems to have been so concerned with the drag forces produced by air resistance, admittedly an important effect for falling feathers, leaves, snowflakes, and other light objects that also offer an unusual amount of surface area for the air to push up against, that he forgot to test his theory on more typical objects like rocks and bricks and shoes, things that are compact and heavy. In other words, he focused too much on the noise air resistance and not enough on the signal inertia and gravity. Galileo didn't let himself be distracted. He knew that air resistance and friction were inescapable in the real world, as in his experiment, but they were not of the essence. Anticipating the criticism that he overlooked them in his analysis, he conceded that a pellet of birdshot does not fall quite as fast as a cannonball, but noted that the error incurred is much, much less than that produced by Aristotle's theory. In the dialogue of 2 New Sciences, Galileo's surrogate urges his simple-minded Aristotelian questioner not to divert the discussion from its main intent and fasten upon some statement of mine which lacks a hair's breadth of the truth, and under this hair hide the fault of another which is as big as a ship's cable. That's the point. In science, being off by a hair's breadth is acceptable, being off by a ship's cable is not. Galileo went on to study projectile motion, like the flight of a musket ball or a cannonball. What sort of arc do they follow? Galileo had the idea that a projectile's motion was compounded of 2 different effects that could be treated separately. A motion sideways parallel to the ground, for which gravity played no part, and a vertical motion upward or downward, on which gravity acted and his law of falling bodies applied. Putting those two kinds of motion together, he discovered that projectiles follow parabolic paths. You see them whenever you play a game of catch or take a drink from a water fountain. This was another stunning connection between nature and math, and a further clue that the book of nature is written in the language of mathematics. Galileo was elated to discover that a parabola, an abstract curve studied by his hero Archimedes, was out there in the real world. Nature was using geometry. To arrive at this insight, however, Galileo again had to know what to neglect. As before, he had to ignore air resistance, the effect of drag on the projectile as it moves through the air. That frictional effect would slow the projectile down. For some kinds of projectiles, a thrown rock, friction is negligible compared to gravity. For others, a beach ball or a ping-pong ball, it is not. All forms of friction, including drag caused by air resistance, are subtle and difficult to study. To this day, friction remains mysterious and is a topic of active research. To get the simple parabola, Galileo needed to assume the sideways motion would continue forever and never slow down. This was an instance of his law of inertia, which states that a body in motion stays in motion at the same speed and in the same direction unless acted on by an outside force. For a real projectile, air resistance would be that outside force. But in Galileo's mind, it was better to start by ignoring it, to capture the lion's share of the truth and the beauty of how things move, from a swinging chandelier to the global positioning system. Legend has it that Galileo made his first scientific discovery when he was a teenage medical student. One day, while attending a mass at the Cathedral of Pisa, he noticed a chandelier swaying overhead, moving to and fro like a pendulum. Air currents kept jostling it, and Galileo observed that it always took the same time to complete its swing, whether it traversed a wide arc or a small one. That surprised him. How could a big swing and a little swing take the same amount of time? But the more he thought about it, the more it made sense. When the chandelier made a big swing, it traveled farther, but it also moved faster. Maybe the two effects balanced out. To test this idea, Galileo timed the swinging chandelier with his pulse. Sure enough, every swing lasted the same number of heartbeats. This legend is wonderful, and I want to believe it, but many historians doubt it happened. It comes down to us from Galileo's first and most devoted biographer, Vincenzo Viviani. As a young man, he had been Galileo's assistant and disciple near the end of the older man's life, when Galileo was completely blind and under house arrest. In his understandable reverence for his old master, Viviani was known to have embellished a tale or two when he wrote Galileo's biography years after his death. But even if the story is apocryphal, and it may not be, we do know for sure that Galileo performed careful experiments with pendulums as early as 1602, and that he wrote about them in 1638 in Two New Sciences. In that book, which is structured as a Socratic dialogue, one of the characters sounds like he was right there in the cathedral with the dreamy young student. Thousands of times I have observed vibrations, especially in churches where lamps, suspended by long cords, had been inadvertently set into motion. The rest of the dialogue expounds on the claim that a pendulum takes the same amount of time to traverse an arc of any size. So we know that Galileo was thoroughly familiar with the phenomenon described in Viviani's story. Whether he actually discovered it as a teenager is anybody's guess. In any case, Galileo's assertion that a pendulum's swing always takes the same amount of time is not exactly true. Bigger swings take a little longer, but if the arc is small enough, less than 20 degrees, say, it's very nearly true. This invariance of tempo for small swings is known today as the pendulum's isochronism, from the Greek words for equal time. It forms the theoretical basis for metronomes and pendulum clocks, from ordinary grandfather clocks to the towering clock used in London's Big Ben. Galileo himself designed the world's first pendulum clock in the last year of his life, but he died before it could be built. The first working pendulum clock appeared 15 years later, invented by the Dutch mathematician and physicist Christiaan Huygens. Galileo was particularly intrigued and frustrated by a curious fact he discovered about pendulums: the elegant relationship between its length and its period, the time it takes the pendulum to swing once back and forth. As he explained, if one wishes to make the vibration time of one pendulum twice that of another, he must make its suspension 4 times as long. Using the language of proportions, he stated the general rule. For bodies suspended by threads of different lengths, he wrote, the lengths are to each other as the squares of the times. Unfortunately, Galileo never managed to derive this rule mathematically. It was an empirical pattern crying out for a theoretical explanation. He worked at it for years but failed to solve it. In retrospect, he couldn't have. Its explanation required a new kind of mathematics beyond any that he or his contemporaries knew. The derivation would have to wait for Isaac Newton and his discovery of the language God talks, the language of differential equations. Galileo conceded that the study of pendulums may appear to many exceedingly arid, although it was anything but that, as later work showed. In mathematics, pendulums stimulated the development of calculus through the riddles they posed. In physics and engineering, pendulums became paradigms of oscillation. Like the line in William Blake's poem about seeing the world in a grain of sand, physicists and engineers learned to see the world in a pendulum's swing. The same mathematics applied wherever oscillations occurred. The worrisome movements of a footbridge, the bouncing of a car with mushy shock absorbers, the thumping of a washing machine with an unbalanced load, the fluttering of Venetian blinds in a gentle breeze, the rumbling of the earth in the aftershock of an earthquake, the 60-cycle hum of fluorescent lights. Every field of science and technology today has its own version of to and fro motion, of rhythmic return. The pendulum is the granddaddy of them all. Its patterns are universal. Arid is not the right word for them. In some cases, the connections between pendulums and other phenomena are so exact that the same equations can be recycled without change. Only the symbols need to be reinterpreted. The syntax stays the same. It's as if nature keeps returning to the same motif again and again, a pendular repetition of a pendular theme. For example, the equations for the swinging of a pendulum carry over without change to those for the spinning of generators that produce alternating current and send it to our homes and offices. In honor of that pedigree, electrical engineers refer to their generator equations as swing equations. The same equations pop up yet again, Zelig-like, in the quantum oscillations of a high-tech device that's billions of times faster and millions of times smaller than any generator or grandfather clock. In 1962, Brian Josephson, then a 22-year-old graduate student at the University of Cambridge, predicted that at temperatures close to absolute zero, pairs of superconducting electrons could tunnel back and forth through an impenetrable insulating barrier, a nonsensical statement according to classical physics. Yet calculus and quantum mechanics summoned these pendulum-like oscillations into existence, or to put it less mystically, they revealed the possibility of their occurrence. 2 years after Josephson predicted these ghostly oscillations, the conditions needed to conjure them were set up in the laboratory, and indeed there they were. The resulting device is now called a Josephson junction. Its practical uses are legion. It can detect ultra-faint magnetic fields 100 billion times weaker than that of the Earth, which helps geophysicists hunt for oil deep underground. Neurosurgeons use arrays of hundreds of Josephson junctions to pinpoint the sites of brain tumors and locate the seizure-causing lesions in patients with epilepsy. The procedures are entirely non-invasive, unlike exploratory surgery. They work by mapping the subtle variations in magnetic field produced by abnormal electrical pathways in the brain. Josephson junctions could also provide the basis for extremely fast chips in the next generation of computers and might even play a role in quantum computation, which will revolutionize computer science if it ever comes to pass. Pendulums also gave humanity the first way to keep time accurately. Until pendulum clocks came along, the best clocks were pitiful. They would lose or gain 15 minutes a day, even under ideal conditions. Pendulum clocks could be made 100 times more accurate than that. They offered the first real hope of solving the greatest technological challenge of Galileo's era, finding a way to determine longitude at sea. Unlike latitude, which can be ascertained by looking at the sun or the stars, longitude has no counterpart in the physical environment. It is an artificial, arbitrary construct, but the problem of measuring it was real. In the age of exploration, sailors took to the oceans to wage war or conduct trade, but they often lost their way or ran aground because of confusion about where they were. The governments of Portugal, Spain, England, and Holland offered vast rewards to anyone who could solve the longitude problem. It was a challenge of the gravest concern. When Galileo was trying to devise a pendulum clock in his last year of life, he had the longitude problem firmly in mind. He knew, as scientists had known since the 1500s, that the longitude problem could be solved if one had a very accurate clock. A navigator could set the clock at his port of departure and carry his home time out to sea. To determine the ship's longitude as it traveled east or west, the navigator could consult the clock at the exact moment of local noon, when the sun was highest in the sky. Since the Earth spins through 360 degrees of longitude in a 24-hour day, each hour of discrepancy between local time and home time corresponds to 15 degrees of longitude. In terms of distance, 15 degrees translates to a whopping 1,000 miles at the equator. So for this scheme to have any hope of guiding a ship to its desired destination, give or take a few miles of tolerable error, a clock had to run true to within a few seconds a day. And it had to maintain this unwavering accuracy in the face of heaving seas and violent fluctuations in air pressure, temperature, salinity, and humidity, factors that could rust a clock's gears, stretch its springs, or thicken its lubricants, causing it to speed up, slow down, or stop. Galileo died before he could build his clock and use it to tackle the longitude problem. Christian Huygens presented his pendulum clocks to the Royal Society of London as a possible solution, but they were judged unsatisfactory because they were too sensitive to disturbances in their environment. Huygens later invented a marine chronometer whose tick-tock oscillations were regulated by a balance wheel and a spiral spring instead of a pendulum, an innovative design that paved the way for pocket watches and modern wristwatches. In the end, however, the longitude problem was solved by a new kind of clock, developed in the mid-1700s by John Harrison, an Englishman with no formal education. When tested at sea in the 1760s, his H4 chronometer tracked longitude to an accuracy of 10 miles, sufficient to win the British Parliament's prize of £20,000, equivalent to a few $1,000,000 today. In our own era, the challenge of navigating on Earth still relies on the precise measurement of time. Consider the global positioning system. Just as mechanical clocks were the key to the longitude problem, atomic clocks are the key to pinpointing the location of anything on Earth to within a few meters. An atomic clock is a modern-day version of Galileo's pendulum clock. Like its forebear, it keeps time by counting oscillations, but instead of tracking the movements of a pendulum bob swinging back and forth, an atomic clock counts the oscillations of cesium atoms as they switch back and forth between two of their energy states, something they do 9,192,631,770 times per second. Though the mechanism is different, the principle is the same. Repetitive motion back and forth can be used to keep time, and time in turn can determine your location. When you use the GPS in your phone or car, your device receives wireless signals from at least 4 of the 24 satellites in the global positioning system that are orbiting about 12,000 miles overhead. Each satellite carries 4 atomic clocks that are synchronized to within a billionth of a second of one another. The various satellites visible to your receiver send it a continuous stream of signals, each of which is time-stamped to the nanosecond. That's where the atomic clocks come in. Their tremendous temporal precision gets converted into the tremendous spatial precision we've come to expect from GPS. The calculation relies on triangulation, an ancient geolocation technique based on geometry. For GPS, it works like this. When the signals from the 4 satellites arrive at the receiver, your GPS gadget compares the time they were received to the time they were transmitted. Those 4 times are all slightly different, because the satellites are at 4 different distances away from you. Your GPS device multiplies those 4 tiny time differences by the speed of light to calculate how far away you are from the 4 satellites overhead. Because the positions of the satellites are known and controlled extremely accurately, your GPS receiver can then triangulate those 4 distances to determine where it is on the surface of the Earth. It can also figure out its elevation and speed. In essence, GPS converts very precise measurements of time into very precise measurements of distance, and thereby into very precise measurements of location and motion. The global positioning system was developed by the US military during the Cold War. The original intent was to keep track of US submarines carrying nuclear missiles and give them precise estimates of their current locations, so that if they needed to launch a nuclear strike, they could target their intercontinental ballistic missiles very accurately. Peacetime applications of GPS nowadays include precision farming, blind landings of airplanes in heavy fog, and enhanced 911 systems that automatically calculate the fastest routes for ambulances and fire trucks. But GPS is more than a location and guidance system. It allows time synchronization to within 100 nanoseconds, which is useful for coordinating bank transfers and other financial transactions. It also keeps wireless phone and data networks in sync, allowing them to share the frequencies in the electromagnetic spectrum more efficiently. I've gone into all this detail because GPS is a prime example of the hidden usefulness of calculus. As is so often the case, calculus operates quietly behind the scenes of our daily lives. In the case of GPS, almost every aspect of the functioning of the system depends on calculus. Think about the wireless communication between satellites and receivers. Calculus predicted the electromagnetic waves that make wireless possible through the work of Maxwell that we discussed earlier. Without calculus, there'd be no wireless and no GPS. Likewise, the atomic clocks on the GPS satellites use the quantum mechanical vibrations of cesium atoms. Calculus underpins the equations of quantum mechanics and the methods for solving them. Without calculus, there'd be no atomic clocks. I could go on. Calculus underlies the mathematical methods for calculating the trajectories of the satellites and controlling their locations, and for incorporating Einstein's relativistic corrections to the time measured by atomic clocks as they move at high speeds and in weak gravitational fields. But I hope the main point is clear. Calculus enabled the creation of much of what made the global positioning system possible. Calculus didn't do it on its own, of course. It was a supporting player, but an important one. Along with electrical engineering, quantum physics, aerospace engineering, and all the rest, calculus was an indispensable part of the team. So let's return to young Galileo sitting in the Cathedral of Pisa pondering that chandelier swinging back and forth. We can see now that his idle thoughts about pendulums and the equal times of their swings had an outsized impact on the course of civilization, not just in his own era but in our own. Kepler and the mystery of planetary motion. What Galileo did for the motion of objects on Earth, Johannes Kepler did for the motion of the planets in the heavens. He solved the ancient riddle of planetary motion and fulfilled the Pythagorean dream by showing that the solar system was ruled by a kind of celestial harmony. Like Pythagoras with his plucked strings and Galileo with his pendulums, projectiles, and falling bodies, Kepler discovered that planetary motions follow mathematical patterns. And like Galileo, he was enthralled by the patterns he glimpsed, and yet frustrated that he couldn't explain them. Also like Galileo, Kepler was born into a family on the way down, but his circumstances were far worse. His father was a drunken mercenary soldier, criminally inclined, as Kepler recalled, and his mother was perhaps understandably bad-tempered. On top of that, Kepler contracted smallpox as a child and nearly died from it. His hands and vision were permanently damaged, which meant he could never have a physically strenuous job as an adult. Fortunately, he was bright. As a teenager, he learned mathematics and Copernican astronomy at Tübingen, where he was recognized as having such a superior and magnificent mind that something special may be expected of him. After receiving his master's degree in 1591, Kepler studied theology at Tübingen and planned to become a Lutheran minister. But when a math teacher at the Lutheran school in Graz died and the church authorities called for a substitute, Kepler was chosen, and he reluctantly gave up the idea of a life in the clergy. Nowadays, all students of physics and astronomy learn about Kepler's 3 laws of planetary motion. What is often left out is the story of his agonizing, almost fanatical struggle to uncover those laws. He spent decades toiling, searching for regularities, propelled by mysticism and his faith that there had to be some divine order in the nightly positions of Mercury, Venus, Mars, Jupiter, and Saturn. A year after his arrival in Graz, a secret of the cosmos was revealed to him, he believed. One day while teaching his class, he suddenly had a vision of how the planets must arrange themselves around the sun. The idea was that the planets were carried by celestial spheres nested inside one another, like Russian dolls, with the distances between them dictated by the 5 Platonic solids: the cube, tetrahedron, octahedron, icosahedron, and dodecahedron. Plato had known and Euclid had proved that no other 3-dimensional shapes could be built from identical regular polygons. To Kepler, their uniqueness and symmetry seemed fit for eternity. He performed his calculations intensely, feverishly. Day and night I was consumed by the computing to see whether this idea would agree with the Copernican orbits, or if my joy would be carried away by the wind. Within a few days everything worked, and I watched as one body after another fit precisely into its place among the planets. He circumscribed an octahedron about the celestial sphere of Mercury and placed the sphere of Venus through its corners. Then he circumscribed an icosahedron about the sphere of Venus and placed the sphere of Earth through its corners, and so on with the other planets, interlocking the celestial spheres and Platonic solids like a 3-dimensional puzzle. He depicted the resulting system in a cutaway drawing in his Cosmic Mystery of 1596. His epiphany explained so much. Just as there were only 5 Platonic solids, there were only 6 planets, including the Earth, and hence 5 gaps between them. Everything made sense. Geometry ruled the cosmos. He had wanted to become a theologian, and now he could write with satisfaction to one of his mentors, "Behold how through my effort God is being celebrated in astronomy." Actually, the theory didn't quite match the data, particularly as regards the positions of Mercury and Jupiter. That mismatch meant something was wrong, but what was it? His theory, the data, or both? Kepler suspected the data might be wrong, but he didn't insist on the correctness of his theory, which was wise in retrospect since the theory had no chance of success. As we now know, there are more than 6 planets. Nevertheless, he didn't give up. He continued to ponder the planets and soon got a break when Tycho Brahe asked him to be his assistant. Tycho, as historians always call him, was the world's best observational astronomer. His data were 10 times more accurate than any obtained previously. In the days before the invention of the telescope, he devised special instruments that allowed him, with the naked eye, to resolve the angular positions of the planets to within 2 arcminutes. That's 1/30th of a degree. To get a sense of what a tiny angle this is, imagine looking up at the full moon on a clear night while holding your little finger all the way out in front of your face. Your little finger turns out to be about 60 arcminutes wide, and the moon is about half that. So when we say Tycho could resolve 2 minutes of arc, that means if you drew 30 evenly spaced dots across the width of your little finger, or 15 across the moon, Tycho could see the difference between one dot and the next. After Tycho died in 1601, Kepler inherited his trove of data on Mars and the other planets. To explain their motion, he tried one theory after another, allowing the planets to move in epicycles in various egg-shaped orbits and in eccentric circles with the Sun slightly off-center. But all produced discrepancies with Tycho's data that couldn't be ignored. "Dear reader," he lamented after one such calculation, "if you are tired by this tedious procedure, take pity on me, for I carried it out at least 70 times. Kepler's first law. Elliptical orbits. In his search to explain the motions of the planets, Kepler eventually tried a well-known curve called an ellipse. Like Galileo's parabola, ellipses had been studied in antiquity. As we saw in Chapter 2, the ancient Greeks had defined ellipses as the oval-shaped curves formed by cutting through a cone with a plane at a shallow angle, less steep than the slope of the conical surface itself. If the tilt of the cutting plane is shallow, the resulting ellipse is almost circular. At the other extreme, if the tilt of the plane is only slightly less than the tilt of the conical surface, the ellipse is very long and thin, like the shape of a cigar. If you adjust the tilt of the plane, an ellipse can be morphed from very round to very squashed or anywhere in between. Another way to define an ellipse is in down-to-earth terms and with the help of a few household items. Get a pencil, a corkboard, a sheet of paper, 2 pushpins and a piece of string. Place the paper on the corkboard. Pin the ends of the string down through the paper, making sure to leave some slack in the string. Then pull the string taut with the pencil and begin drawing a curve, keeping the string taut as you move the pencil. After the pencil has gone around both pins and returned to its starting point, the resulting closed curve is an ellipse. The locations of the pins play a special role here. Kepler named them the foci or focal points of the ellipse. They are as meaningful to an ellipse as the center is to a circle. A circle is defined as a set of points whose distance from a given point, its center, is constant. Likewise, an ellipse is a set of points whose combined distance from 2 given points, its foci, is constant. In the string and pushpin construction, that constant combined distance is precisely the length of the loose string between the pins. Kepler's first great discovery, and this time he really did get it right and didn't need to revise his ideas, is that all the planets move in elliptical orbits. Not circles or circles compounded with circular epicycles, as Aristotle, Ptolemy, Copernicus, and even Galileo had thought. No, ellipses. Moreover, he found that for every planet, the Sun was located at one of the foci of the planet's elliptical orbit. It was astonishing, just the sort of holy clue Kepler had been hoping for. The planets were moving in accordance with geometry. It hadn't turned out to be the geometry of the 5 Platonic solids as he'd originally guessed, but his instincts had been right nonetheless. Geometry did rule the heavens. Kepler's second law, equal areas in equal times. Kepler found another regularity in the data. Whereas the first one was about the paths of the planets, this one was about their speeds. Known today as Kepler's second law, it says that an imaginary line drawn from a planet to the Sun sweeps out equal areas in equal intervals of time as the planet goes around in its orbit. To clarify what this law means, suppose we look at where Mars is tonight in its elliptical orbit. Connect that point to the Sun with a straight line. Sun-planet radius. Now think of this line as being something like the blade of a windshield wiper with the Sun at the pivot point and Mars at the tip of the wiper, except the wiper doesn't oscillate back and forth like a real windshield wiper. It always advances, and it does so very, very slowly. As Mars travels forward in its orbit on subsequent nights, the wiper moves along with it and thereby sweeps out an area inside the ellipse. If we look at Mars again sometime later, say after 3 weeks, the slow-moving wiper will have swept out a shape called a sector. What Kepler discovered is that the area of a 3-week sector always stays the same no matter where Mars happens to be in its orbit around the Sun. And there's nothing special about 3 weeks. If we look at Mars at any 2 points in its orbit separated by equal amounts of time, the resulting sectors will always have equal areas, no matter where they are in the orbit. In a nutshell, the second law says that the planets do not move at a constant speed. Instead, the closer they get to the Sun, the faster they move. The statement about equal areas in equal times is a way of making this precise. If time from Pone to Petwo equals time from P3 to Fur, their sectors have equal areas. How did Kepler measure the area of an elliptical sector, given that it had a curved side? He did what Archimedes would have done. He sliced the sector into lots of thin slivers and approximated them with triangles. Next, he computed the areas of the triangles easy, because all their sides are straight, and added them together, integrating them to estimate the area of the original sector. In effect, he used an Archimedean version of integral calculus and applied it to real data. Kepler's third law and the sacred frenzy. The laws that we've discussed so far, each planet moves in an ellipse with the Sun at a focus, and each planet sweeps out equal areas in equal times, are about the planets individually. Kepler discovered both these laws in 1609. In contrast, it took him another 10 years to discover his third law, which is about all the planets collectively. It binds the whole solar system into a single numerological pattern. It came to him after months of furiously renewed calculations, and more than 20 years after his agonizing near miss with the Platonic solids. In the preface to Harmonies of the World, 1619, he wrote in ecstasy about finally seeing the pattern in God's plan. Now, since the dawn 8 months ago, since the broad daylight 3 months ago, and since a few days ago, when the full sun illuminated my wonderful speculations, nothing holds me back. I yield freely to the sacred frenzy. The numerological pattern that enraptured Kepler was his discovery that the square of the period of revolution of a planet is proportional to the cube of its average distance from the Sun. Equivalently, the number t squared divided by a cubed is the same for all the planets. Here t measures how long it takes a planet to go around the Sun once a year for the Earth, 1.9 years for Mars, 11.9 years for Jupiter, and so on, while it measures how far away the planet is from the Sun. That's a bit tricky to define, because the actual distance changes from week to week as a planet moves in its elliptical orbit. Sometimes it's closer to the Sun and sometimes it's farther away. To account for this effect, Kepler defined as the average of the planet's nearest and farthest distances to the Sun. The gist of the third law is simple. The farther a planet is from the Sun, the slower it moves and the longer it takes to complete its orbit. But what's interesting and subtle about this law is that the orbital period is not simply proportional to the orbital distance. For example, our nearest neighbor, Venus, has a period that's 61.5% as long as our year, yet its average distance from the Sun is 72.3% of ours, not 61.5%, as one might naively expect. That's because period squared is proportional to distance cubed, not squared. And so the relationship between period and distance is more complicated than a direct proportion. When t and r are expressed as percentages of Earth years and Earth distances, as above, Kepler's third law simplifies to t squared equals a cubed. It becomes an equation instead of a mere proportionality. To see how well it works, plug in the numbers for Venus. T squared equals 0.615 squared is approximately 0.378, whereas a cubed equals 0.723 cubed is approximately 0.378. So the law holds to 3 significant figures. That's what got Kepler so excited. It's equally impressive when applied to the other planets. Kepler and Galileo, the same and not the same. Kepler and Galileo never met, but they corresponded about their Copernican views and the discoveries they were making in astronomy. When some people refused to look through Galileo's telescope, fearing the instrument was the work of the devil, Galileo wrote to Kepler in a tone of amused resignation. "My dear Kepler, I wish we could laugh at the extraordinary stupidity of the mob. What say you about the foremost philosophers of this university, who with the obstinacy of a stuffed snake, and despite my attempts and invitations 1,000 times, they have refused to look at the planets or the moon or my telescope?" In some ways, Kepler and Galileo were alike. Both were fascinated by motion. Both worked on integral calculus, Kepler on the volumes of curved shapes like wine barrels, Galileo on centers of gravity of paraboloids. In this, they channeled the spirit of Archimedes, carving solid objects in their minds into imaginary thin wafers, like so many slices of salami. Yet in other ways, they were complementary to each other. Most obviously, they were complementary in their greatest scientific contributions, Galileo for the laws of motion on Earth, Kepler for the laws of motion in the solar system. But the complementarity goes deeper, down to scientific style and disposition. Where Galileo was rational, Kepler was mystical. Galileo was the intellectual descendant of Archimedes, entranced by mechanics. In his first publication, he gave the first plausible account of the Eureka legend by showing how Archimedes could have used a balance and a bathtub to determine that King Hiero's crown was not made of pure gold, and to calculate the precise amount of silver that the thieving goldsmith had mixed in. Galileo continued to elaborate on Archimedes' work throughout his career, often by extending his mechanics from equilibrium to motion. Kepler, however, was more the heir to Pythagoras. Fiercely imaginative and with a numerological cast of mind, he saw patterns everywhere. He gave us the first explanation for why snowflakes form six-cornered shapes. He pondered the most efficient way to pack cannonballs and guessed, correctly, that the optimal packing arrangement is the same one that nature uses to pack pomegranate seeds and that grocers use to stack oranges. Kepler's obsession with geometry, both sacred and profane, verged on the irrational, but his fervor made him who he was. As the writer Arthur Koestler astutely observed, Johannes Kepler became enamored with the Pythagorean dream, and on this foundation of fantasy, by methods of reasoning equally unsound, built the solid edifice of modern astronomy. It is one of the most astonishing episodes in the history of thought, and an antidote to the pious belief that the progress of science is governed by logic. Storm clouds gathering. Like all great discoveries, Kepler's laws of planetary motion in the heavens and Galileo's laws of falling bodies on Earth raised many more questions than they answered. On the scientific side, it was natural to ask about ultimate causes. Where did the laws come from? Did a deeper truth underlie them? For example, it seemed too coincidental that the Sun occupied such a special position in all the planetary ellipses, always residing at a focus. Did that mean the Sun was affecting the planets somehow, influencing them through some kind of occult force? Kepler thought so. He wondered if magnetic emanations, recently studied by William Gilbert in England, might be pulling on the planets. Whatever it was, an unknown, invisible force seemed to be acting at great distances across the emptiness of space. The work of Galileo and Kepler also raised questions for mathematics. In particular, curves were back in the limelight. Galileo had shown that the arc of a projectile was a parabola, and Aristotle's circles had now given way to Kepler's ellipses. Other scientific and technological advances of the early 1600s only heightened the interest in curves. In optics, the shape of a curved lens determined how much an image was magnified, or distorted, or blurred. Those were vital considerations for the design of telescopes and microscopes, the hot new instruments that were revolutionizing astronomy and biology, respectively. The French polymath René Descartes asked, could a lens be designed to be free of all blurring? It amounted to a question about curves. What curved shape would a lens need to have so that all the rays of light emanating from a single point, or traveling parallel to one another, would be guaranteed to converge at another unique point after passing through the lens? Curves, in turn, raised questions about motion. Kepler's second law implied that the planets moved non-uniformly around their ellipses, sometimes hesitating, sometimes accelerating. Likewise, Galileo's projectiles moved at ever-changing speeds on their parabolic arcs. They slowed down as they climbed, paused at the top, then sped up as they fell back to Earth. The same was true for pendulums. They slowed down as they climbed to the ends of their arcs, reversed and sped up as they swung through the bottom, then slowed down once again at the other extreme. How could one quantify motions in which speed changed from moment to moment?